Today I briefly want to talk about manifolds, smooth manifolds. But I'll not be proving anything. I just want to give you the intuitive idea about manifolds and why we need them, stuff like that. So, so let me just give you the definition of a manifold. So, so a manifold is a topological space which is Hausdorff second countable and locally Euclidean. So this is the definition of a manifold, but you might not be familiar with these terms: topological space, Hausdorff, and second countable and locally Euclidean. So I'll define these two terms because for now we only need these two. You don't have to know about Hausdorff and second countability for now. You can look it up from Google if you want to, but so we need only these two. So let me just define what a topological space is. A space is set is a topological space if it has a topology tau topology tau endowed in it. So it is a topology tau. Now we have to know what a topology is. So a topology on a set let X be our set, and then a topology X, sorry, tau on X is a collection of subsets of X with the following properties. One, the empty set and the whole set X is in tau. So tau is basically a set whose elements are the subset of X. So the union of any subcollection of tau is in tau, and the intersection of finite subcollection of tau is in tau. So if, so if there is a subset, if there is any set with these following properties, define a topology on X, and the tau being the set of subsets of X. So let me give you an example. So example, let's say our set X is A, B, and C. Then let's consider the power set of X. So the power set of X will have three elements. So one, two. So this is the power set of X. Now let's see if this power set of X define a topology on X or not. So we just have to verify the conditions, the properties. So phi is in phi and X. So this is the whole set X and this is the empty set. So they are in P of X. So first condition satisfied. Second condition, let's take an arbitrary, let's take a subcollection of set, let's say A, B, A, B, and let's take their union. If we take their union, we see that it's just A, B, which is in power set. And if you can verify that if you take any subcollection of these 8 elements and union them and take their union, you will get an element which belongs to the power set of X. So second condition is also satisfied. The third condition, let's take A, B, C, and C, which is the empty set which is in power set of X. So just like the second condition, you can verify it by your own, by taking all the combinations, and you will see that any finite subcollection, the intersection of any finite subcollection is in the set power set of X. So this power set of X define a topology on X because it satisfy all the conditions. So here X is our topological space. Power set of X is our topology. So power set of X is the topology on it. So that's topological space. Now we have to define. So let me give you another example. Let's say R2, and let's say R1. Let's make it. So R1, so it's just a line, minus infinity, infinity, 0. So we can see it can also have a topology. So the whole set is R1, and the subsets will be open sets on R. Now an open set is basically a set is open every element of A has a epsilon neighborhood, and every element of A has a epsilon neighborhood. No, I have to define what the epsilon neighborhood is. So epsilon neighborhood. Let this let's say it's a set A and it's an element. An epsilon neighborhood is an open ball of radius epsilon around, let's say this the point is P. The epsilon neighborhood of around P is B of P. Sorry, P of epsilon. Epsilon is the radius around P, such that so this is the epsilon neighbor, the open ball, and how the way we define it, the element of this is basically P minus Q is less than epsilon. If all Q's such that Q satisfy this condition, P minus Q is less than epsilon. So this is the definition of an open open neighborhood, epsilon neighborhood. Now, what this definition means is every point in the set A has an epsilon neighborhood. An epsilon is an arbitrary number; it can be arbitrarily small. So intuitively, what it means is no matter how close you get, you can always draw an epsilon neighborhood around. Now if I get close, or you can all. So this is what it means intuitively. You can, no matter how close you get to the boundary, try to get close to you will never reach the boundary, because you can always find an epsilon neighborhood around that point. So then the set is called an open set. Now a closed set is closed. A closed set is basically intuitively that we include this boundary. I don't need the definition of a closed set for now. So in R1 we can construct, or we have a topology whose elements are these open sets. In R2, say we have open balls, epsilon, open balls of epsilon. Yes. So this act is the topology on R2 can be defined by the collection of these open subsets. Now let me give you the definition of the local Euclidean means. Is it local Euclidean? is locally Euclidean if there is a map. So there is a homeomorphism. Homeo- there is a homeomorphism phi that phi takes A to Rn. So, so you might not have heard the term about homeomorphism. What homeomorphism is, you all know. So let's say I have this flat surface. Let's a random flat your surface. I can let's say it's a clay. Now you know that you can distort a clay and make a different shape out of it. Let's say we can by distorting it we can make it like this. Then this thing is homeomorphic to this thing, even though they don't look it like it this looks the same. But if we can mold and by molding, if we can make this like this, then we call this two are homeomorphic. So similarly what homeomorphism, so this is exactly what homeomorphism means. But there's that that so if I have to give an uh, a definition, it would go like this. If we have two sets, let's say we have x and y, and they both are topological space. And there is a bijection map, and there is a bijective map f such that then the map f is then f is homeomorphic if the inverse is this. So this is, if this satisfied, then we call the map homeomorphic map. And intuitively, it means what I have what the previous example of the clay, molding the clay. So locally Euclidean means the set U is homeomorphic to Rn. So if this map is a homeomorphic map, then we say the set A is homeomorphic to Rn. So locally Euclidean. So this means what. So this is what it mean by locally Euclidean. If we say it's homeomorphic to Rn, we say it is locally Euclidean. It looks like Rn. Locally it looks like Rn. So now let's. So a manifold is a topological space which is housed of second countable and locally Euclidean. So now we can. So let's see what it means intuitively. Let's see, we have a manifold of dimension m. and let's say it is a let's say there is open set, it is an open set U around the point P. Then if there exists a map such that such that U Rn, then if there is a homeomorphic map between U, homeomorphic map phi, then phi such it is locally Euclidean such that then for if for every p in the manifold we can define an open for every p if there is a neighborhood U such that it is locally Euclidean, then we call it a manifold. So this is a manifold with dimension n. Let's and in the manifold there has to be a manifold is a topological space. So obviously there is a topology in yes, there is a topology in it. So let me give you an example. And the best example I can give you, which you already know, is the sphere, Earth. We all know if we see the Earth from far above, we'll see it is a sphere. But when we walk around, we do not observe the curvature. It seems as though it is a flat surface, but from above it looks like it looks like a sphere. So for a very small portion of it, it is homeomorphic to Rn. That's why a sphere is a manifold of dimension 2. So this is a sphere in R3. Same goal. We can always again give a torus, a donut in R3. If we take a small portion of it, it will look like R2. So like R2. So that's why a torus is a manifold. So a manifold. So I think intuitively it is clear what is a manifold is. Let me move on. So let's see have a manifold. Let's make it bigger. Let's say there is a point P. There is open neighborhood U around P, and there is another open neighborhood V. So P is in the intersection of U and V. So this is the intersection U. Let me give W. So W in V. So now we know that there is a map. Obviously there is a map. There is a map from W to, because it is a manifold, there is a map which is locally, there is a map phi, and it looks like locally Euclidean. So there is a map. So it maps it from W to Rn. There is another map psi, also goes to Rn. Then it will also be defined for this common region. So let me make it here. So W union V. So there is a map phi which takes W union V and maps it to Rn. Say this. There is another map psi and they both looks like Rn. Now we can make another map out of them from this here to here. How the map is defined is we want to take an element from this, and so phi inverse conjugate so composite psi. So psi phi inverse is a map that takes W union V and maps it to that takes phi of W union V and maps it to psi of W union V. So this map is called the chart transition map. Oh, I haven't defined what a chart is. Sorry. So in yes. So here we said that this is an open neighborhood around P with this map psi. So this whole thing U with psi is called a chart because this map takes the open map U and maps it to Rn. Then this open set with this map is called a chart. Here U is called an open coordinate neighborhood. Coordinate. And phi is called an coordinate system. Coordinate system. So here we have two charts, W with phi and here V with psi. And we have seen that by chart transition function we can map we have a map that we have a map from one chart to another chart. But the best example of this is you already know that we can transform a Cartesian space, two-dimensional Cartesian space to polar coordinates by x is equal to x is equal to r cos theta, y is equal to r sin theta. So this is an example of these chart transition functions. So yeah, this. Then let me define what a tangent space is. Let me so a chart so a chart is compatible charts. So a chart is compatible if we know this is one map. We can also take another map from the direction here to here, which will be phi psi inverse. So a chart is compatible if this map and this map both are smooth maps. So C infinity or smooth. C infinity means it's infinitely differentiable, and from now uh, we'll always be talking about compatible charts, and C infinity. All our maps will be C infinity, and charts are will be compatible charts. If we yes, in future uh, we might have to use two charts. Then it will be assumed that they are compatible. Now let me define the tangents. Oh, I forgot to give another. I forgot to talk about another thing. So why do we need this? So why do we need these things, this manifold and everything? So uh, the motivation is we have to use calculus to describe everything, but and we know how to do calculus in Euclidean space. But if the space have a curvature like a sphere, globally we don't know how to do calculus in it. But but we know that a sphere is locally Euclidean, so we can consider a very small portion of it, and because that small portion is locally Euclidean, we can do calculus on it. And by doing these things all over, on every all over the sphere, we can describe we can describe the about the whole space. Even though we cannot do it just by doing calculus globally on it, but if we consider small portions of it, then we can easily describe the features, or can do calculus and describe whatever we want to. And that's why we need all these things. Again, for torus, we don't know how to do calculus in curved things, but if small portion of looks like R2, so and we know how to do calculus in R2, so we can do calculus in that small portion, and we can consider other small portions and do calculus on it and describe the whole space. So that's why we need these things, because not everything in our universe is locally is not our space is not a Euclidean space. The things that interest us. So tangent space. So let's say we have a manifold M, and there is a point P, and there is a curve tracing the point P. Then from calculus we know that at this point there will be tangent line. From calculus we know that there is a tangent line of that curve on that point P. Now there might be many other curves tracing the point P, and for every curve there is a tangent line, and that tangent line belongs and all those tangent line belong to a tangent space. A tangent space looks like, if we consider sphere, then the tangent line will look like R2. So, so this is the idea of a tangent space. So this is an example of sphere R2, but it can be so in general, for an n-dimensional manifold, the tangent space looks like Rm, and we define the tangent space. If the manifold is M, the tangent space is written as a point P. The tangent space of a point P is TPM, and uh, notice that at every point there is a tangent space. That's why we write this at the point, include this point, and the set of all oh no, I'll talk about it later. So this is TPM, the tangent space, and the basis, you know about basis from the previous video, and the basis of the tangent space is TTX1 P, like this, and xn's. Xn's are the functions. Let's say there is a code. Sorry. So we have so yeah, our map. So the chart, the coordinate system is phi, and we know that it takes to Rn. But then we define another map that takes Rn, that project every. Let's say you have a vector v. We know it is a component v of x and v of y. What we can do is define another map x that takes v to vx and y that takes v to vy, and we do a similar thing here. For every component we define a map Ri that projects the vector. I shouldn't call it a vector, but you get the idea. It maps it to the component, and the map xn is defined like this. Alright. Yes. So this is the basis of px1, 2, and p. So this is the basis of the tangent space at point P of M. So we know about dual spaces from the previous video. So if we have so it's clear that TPM looks like Rm. We have a dual space of TPM, which is denoted as TP star of M. It takes an element of TPM and maps it to R. So this is our dual space, and the basis of TP star of M is conforms dx1 at p, dx2 at p, subtracted by dxn at p, and d of x acting on d by dx1 is, in general, let's see, I and j, and then delta ij, and you know why it's because of the condition. Now we want to define what a vector field is. So a vector field is a map X such that X take a point from M and maps it to TPM. Oh, I have to define what TM is here. So TM is nothing but the set of all the TPMs, and P belongs to M. So basically, we know that for every point P there's tangent space, and if we collect all those points, all the tangent space of those points, and the set of all the tangent spaces, yeah, I think it's clear from the definition. So this is the definition of a vector field. Now, at a vector field at a point P, it acts on a function and gives us a number. So this another way to define vector field is x of acts on a function, and it takes take an element from the manifold and gives a real number. Now xp, since xp, x of p is an element of Tm, we can write it as, and we have know that basis of Tm. The basis of Tm is for a point, or for a given point, there will be associate TPM. Can be written as summation of, no, we don't write that. So summation of a function of I, it's x of I, and the basis of TPM dxi at point P. So this, so we can write like this, a vector field. We can write a vector field like as the linear combination of the basis of TPM, and it satisfies some properties. We know that vector field acts on functions, So basically, vector fields x on C infinity functions give us a C infinity function. So function give us a number. So if vector field x on 2 function, it will. So it's the distributive law. Then it follows from the previous one. It follows from one. Then we have the Leibniz rule, and there is a product defined on the C infinity bundle. Then x of f. So this so it gives us infinite function. So this dot uh, is in the multiplication on C infinity ring, and you don't have to know about what a ring is for now. And this is the Leibniz rule. It is familiar. The Leibniz rule is the same as the uh, uh, product rule in calculus. And one form. So the dual notion of a vector field is one form. We know what a vector field does. It takes so a one form is denoted as this d x on a function point, and it takes an element from it takes the vector field and maps to a real number, which is defined as x of f of p or xp f. So this is one form. So this is all I wanted to talk about from manifolds, and I wanted to cover many other things, but I think I shouldn't. Um, let me touch. Let me give you the definition of a tensor. Then I'll talk about tensors in detail in the next video. So definition. Tensor. Let let B be a vector space, then a tensor of type Rs is a multilinear map tensor T multilinear map such that it takes R there are covectors and S vectors, so and it maps to the real number. So this is a tensor. It's a map that takes R vectors and S R covectors and S vectors and maps to a real number. And what multilinearity means is that, let's say, phi plus and v plus lambda, then it can be written as is linear in every slot. This is what it means. It's a tensor of type 1 1. No, not 1 1. It if phi is a covector, if phi is an element of V star, and phi and psi is an element of V star, and V and lambda is an element of V, then this is a 1 1 tensor. If they are also a member of V star, then it's a 0 to 0 tensor. And if both are map element of V, then it says 0 to tensor. So we know that there is another condition I forgot to name. So multilinearity. So I say a map is multilinear if it satisfies this condition and another condition. T of alpha times phi comma v is alpha times T of phi comma v, where alpha is a scalar. Now we know that for a dual space, we know that a function, an element of a dual space takes an element V and maps it to R. Now in our tensor, if we consider 0 covectors and 1 as vectors, then so a tensor of type, if R is 0 and S is equals to 1, then a 0 1 tensor is basically takes V, which is precisely the definition of a map of an element of the dual space. So a 0 1 tensor is basically a dual vector, and there is the dual vector in the dual space of the dual space. So dual space of the dual space will have an element f's such that f takes an element from V star and maps it to real number. And there is a theorem which can be proved that V star star is basically the same as V. So a 1 0 tensor is like V star and takes it to R, then since so this the t is an element of, and we know it is equal to v, so t is is a vector, so t is a vector. That means a 1-0 tensor is a vector. So tensor is basically a a generalized notion of vector and covectors. And I will I'll extensively talk about in the next video. So, and for now, this is all for today. Thanks. And the part about vector fields and tangent space, the vector fields and one forms might not be clear. So I'll talk about it when we discuss about topics which are related to them. So sorry for not covering them in all detailed and rigorously. So yeah, that's for now. Thank you.